All right, so let's continue our implementation. So in terms of contributing a model, basically I'm doing these two steps here, implementing the model in the Hugging Face format and writing the conversion script. I'm doing them in parallel. So basically every Hugging Face model always consists of like the actual model implementation, which is always called modeling and then the name of the model.py, and then there is a configuration which like defines the hyperparameters in terms of the architecture of the model, like the number of layers, number of attention heads, and so on. And so in our conversion script, we basically start by loading the original model. So in this case, we could use the Torch Hub, which is handy. Like we can directly load the original model from Torch Hub, and then here we're loading our Hugging Face model, and then we are basically converting the names of the parameters. So that is contained in this Google Doc here. So basically we need to rename the keys of the state dictionary of the original model to the names that are chosen for the Hugging Face model. So we have already converted the patch embedding layer. So the next step now is to convert these transformer layers. And so every transformer layer always takes in these hidden states, and then will also output hidden states of the same shape. So in this case, we have a sequence length of 257 tokens. So these come from the fact that we have an image resolution of 224 by 224. We divide by the patch size, we square. That's the number of image patches we have in total, which is 256. But then we also add a special CLS token, which is why we add a 1 here. So that's why we have 257 tokens. So yeah, we are now done until here. Now the next step is to do these transformer layers. And so if you look into the original model, you can see like these blocks here. These are exactly these transformer layers, and we have 12 of them. So every layer is actually identical. So yeah, they all consist of a layer norm, then an attention layer. This is layer scale, so that's another trick, a bit like dropout, I think. Then there is another layer norm, a multi-layer perceptron, and finally another layer scale layer. So now we will have to implement this in our Dino V2 Hugging Face implementation. So if you go to the Dino V2 model itself, so we have our patch embedding layer, and then we have the encoder. And as you can see here, this encoder class consists of a list of Dino V2 layers. So these Dino V2 layers are exactly these transformer layers that we will need to implement. And then as you can see, each Dino V2 layer consists of a attention layer, as well as 2 layer norms, as you can see here. And then some other classes, which are actually multi-layer perceptrons, like linear transformations. So basically now we will have to see whether our Dino V2 layer, well, probably we're gonna need to implement or add the layer scale, because I'm not seeing that here for now, and that's something that's quite unique to Dino V2. So let's see here in the forward features method. So here, yeah, we're sending, as you can see, first we create the patch embeddings from our pixel values, and now we send them through each of these 12 transformer layers, or blocks as they are called here. So the blocks here, they are a module list. I don't think block chunks is being used here. Block chunks is set to 1. Let's see whether block chunks, okay, here they are set to 0. So they're actually not used. So we're here, blocks list, block function. Okay, and so the block function I use is a memory efficient attention variant. Okay, but yeah, that one relies on the Xformer package. So Xformers is like a package created by MetaAI for efficiently running transformers. It's a pretty nice optimization package. But yeah, when we were running the original model, we got like a warning. Xformer is not available. So yeah, it also runs fine if you don't have it. As you can see here, if it's not available, then it's just gonna run the for method of the superclass, which is the attention class. So yeah, this class corresponds to the, yeah, this is the attention that we will have to implement. So this seems like a regular attention class. So this one is probably gonna be similar as our Dino v2 attention class here. This is gonna be very similar. So we have our queries key value projection layer, a dropout layer, and then a final linear layer followed by another dropout layer. But then we have this block class. Okay, so here you see the attention being defined, layer norm, and so on. Let's go back to the Dino v2 layer class. Well, here I called layer norm before, layer norm after. I'm just gonna call them norm 1, norm 2. I'm gonna remove that copied from statement. Okay, so we have a first layer norm, then the attention layer, then we have the layer scale thing. Okay, I'm gonna make it very similar. So then we have our layer scale followed by a drop path layer. So let's call this, let's give it a better name, layer scale 1. Yeah, we'll have to implement these classes. And then we have a second layer norm, followed by a feed4 neural network layer, self.mlp. Yeah, I'm gonna say here to do MLP layer. Followed by a layer scale. Layer scale 2. So let's see here, this corresponds to the block class in the original implementation. Yeah, we could of course also call them layer norm before and layer norm after. I think I can remove this. Let's see how this layer scale class is defined. Yeah, this is taken from the TIM. I'm just gonna copy this and I'm gonna add it here, probably above the relevant class. And so typically also something that what we do is like we add a prefix of the name of the model. And also we prefer to have like clear variable names, so let's call them here hidden state instead of x. And then we can say here Dino v2 layer scale. Now the dim will be config.hidden size here. So the dimension is just the hidden size here, which is 768. And then there's drop path. Okay, but actually we already have quite a lot of classes in the transformers library which use drop path. Oh. Yeah, like this one. Bait drop path. So what we can actually just do is So we're gonna call this dyno v2 drop path config.drop path rate. And then here we can include a new class. And now thanks to this copied from, we can actually just include here copied from transformers.models.bait.modeling bait.bait drop path. Alright, now I'm gonna showcase this copied from. So if you now run make fix copies, it's gonna copy over the entire implementation here. So let's see whether that works fine. Okay, so now it has included this. And then yeah, we will also need this thing here. I'm also going to check whether nothing else has been messed up. Looks like it's fine. So as you can see, this copied from mechanism is quite handy. Okay, so every transformer layer consists of a first layer norm and an attention layer, first layer scale. So here this init values thing. Let's see what they define here. It's set to none here. For layer scale, none or 0. No layer scale. Okay, so it might be that they don't even use layer scale, but it's present, it seems, in the it's present as a parameter. Layer scale.gamma. Okay, maybe let's see here init values. Oh, here they set init values to 1. So I'm gonna create like a new attribute in the configuration. So yeah, encoder stride here is actually also something I need to remove. Let's call it init values as well for now. So there should be a float and it defaults to 0.1. And then here we can, for the layer scale, say config.init values. And then yeah, this drop path rate also still needs to be added here. I'm gonna check what drop path rate they use. By default it's set to 0 here. Okay, so yeah, I'm gonna add the possibility to do drop path, which is a bit like dropout. It's like a regularization technique. Yeah, GitHub Copilot would have been very handy here, but currently running on a remote machine and would have to look into adding GitHub Copilot there. But probably we have a drop path rate here as well, yeah, so I can actually use it. And it's defaulting to 0.0. All right, and then we can say here config.dropPath rate. Actually gonna see if there is already another model with layer scale. Probably there is. Use layer scale value. FocalNet has it. Layer scale value. Yeah, might be a better name actually. And init values. I'm gonna rename that. Yeah, init values here can be and then in the configuration, let's call it layer scale value. All right. So yeah, the only thing we also need to implement the multi-layer perceptron here. Okay, so let's go back to our block class here. Sample drop ratio, what's that? Okay, I'm gonna see whether they have used this. Defaults to 0 here. Seems that they have a lot of drop pad stuff added. Yeah, we can maybe add that later on, but for now, let's just focus on our on our transformer layer. So yeah, let's add maybe the multi-layer perceptron as well. Feed forward neural network layer. It's default to MLP. Okay, and what does MLP mean? Okay, so if an feed forward neural network layer is equals to MLP, then use this class. Okay, so I'm just gonna copy over this class here. And again, we're gonna call it Dino v2. Maybe let's call it MLP like so. And then here I can just say self MLP is equal to, and then config dot hidden size. Oh yeah, this actually, let's see. In features, hidden features, out features. In features equals to dim. Okay. So yeah, the in features here is equal to config.hidden size, but then the intermediate features is the MLP hidden dimension. And this is oftentimes equal to config.hidden size times config. Or is it divided by, wait, I need to see. What is it? Yeah. Let's call it MLP hidden size to be consistent. And then the out features. Okay, there are no out features being specified. Here again, let's call this hidden state instead of X. To give some better variable names. Let's go back to the Dino v2 MLP class. That's not really nice here, callable. We don't want this. Act layer. It's defaulting to in.gelu activation function. Okay. Yeah, I'm just gonna do this. Oh. I'm gonna remove this thing here and just hard code this, because that's like, yeah, more logical, I would say. Okay, so then we have implemented our Dino v2 multi-layer perceptron layer, which is used in the transformer layer. So yeah, basically, if you go back to our figure here, so every transformer layer here, it consists of like 2 layer norms, 1 MLP, and 1 attention layer. That's what we have implemented now with this layer here, and that's just repeated a bunch of times. Like the base Dino v2 model will repeat this class 12 times. So basically the hidden states go through 12 individual transformer layers. So let's see where Dino v2 layer is being called. So yeah, the Dino v2 encoder is then actually this part here, which repeats the transformer layers a bunch of times. So they are repeated config.number of hidden layers. So here number of hidden layers is going to default to 12 because we have 12 transformer layers, as you can see here. Oh yeah, intermediate size. Well, I'm just going to call it MLP ratio, which is set to 4 typically. And then the hidden act, I'm not sure it's being used actually. Yeah, the Dino v2 intermediate class, I'm gonna skip that one. We're not using it. Same with the Dino v2 output class. Dino v2 self attention is being used. Dino v2 self output is also being used. Dino v2 layer. Alright, so now comes the interesting part where we need to basically convert our transformer layer. Well, we need to convert the original transformer layer weights and biases to the parameters of our transformer layer. So now let's see, so if we instantiate our Dino v2 model, like so, then we can like again print out the various parameters. So let's see, a single transformer layer looks like this. So let's go back to our Google Doc. So this has been a bit updated now, so let's maybe remove this. So now we have this here. So now we need to basically convert this to this. So blocks.0.norm1.weight needs to be converted to these names here. So let's also give them a color. Then we have the tension. So yeah, one thing also that you can see here, as you can see, the query key and value projection is just a single matrix, a single weight and bias in the original implementation, whereas here we split them actually up into separate parameters. So that's a thing we will need to take into account when converting the weights. Then we have our projection layer. I think that corresponds to this layer here, so let's also give that a color, like so. Then we have this layer scale thing here. Let's put that in bold. And then we have our second layer norm. First fully connected, second fully connected, and then a second layer scale. So yeah, as you can see, that's a bit how, so let's maybe give this another color for clarity. So this corresponds to each other, and so on. So yeah, that's what we gonna need to take into account here. So here, yeah, next thing was to do these transformer blocks. So for E and range, config.number of hidden layers. Basically, first let's do the first layer norm. So both the weight and the bias. Need to be converted to encoder.layer.norm1. Alright, so that's to convert the first layer norm. Again, GitHub Copilot would be very handy here because it would like automatically of course, like I have written other conversion scripts where I just like rename blocks to encoder.layer for all the parameters at once. That's like an alternative and way shorter way to convert parameter names. But here for clarity, let's just do it one by one. So we have the layer norms, because like this is also easier actually to debug, because oftentimes when you like change just a prefix for all your parameter names, it might become more difficult to convert. So we have our, well, basically we have now already done this and this. The next thing is our multi-layer perceptron. Yeah, multi-layer perceptron. So like so, and then here. And this will have to be renamed to, yeah, like we could actually also just change the prefix, but for now I'm just gonna do it like so. So then the same thing for the bias, and then the same thing for fully connected to. Then the layer scale. So the layer scale again, well, it was having a bad name, I would say, in the original. Not really clear what ls means. So yeah, blocks.0. And then in our implementation, it has like a longer name, but also it's clearer. So that needs to be done for 2 layer scales. Then the final thing we'll have to do here is to do attention. Well, I think we can already, so these query key and value, okay, we can still do this one here, the projection layer after the attention layer. So let's call it attention projection layer. And then, yeah, so then I can write here the following. So in our case, this projection layer has this name. And then the same thing for the bias. And then, yeah, the only thing we'll have to do are these query keys and values. So now if you run our conversion script again, yeah, that's why we have this separate read and kv function. Has no attribute intermediate. Oh yeah, we still have to implement like the the forward pass. Okay, let's go to the forward pass of our block function. So yeah, first we apply the layer norm, then we apply the attention, and then we apply the layer scale. So first we apply the layer norm, then we apply the attention, And then I think here, tension residual function. Okay, and then we add the residual function, which is like just adding the input back. So I think here we need to apply the first layer scale. Then we have the first residual connection. Again, we apply a second layer norm. Then we apply our multi-layer perceptron, solid.mlp. And then we apply our second layer scale. And then we add our second residual connection. All right. The V2 layer has no outputs. Yeah, that's right. Wait. Second residual connection. So we add, I think it's just gonna be layer output plus, it didn't say it like so, but yeah, again, we will have to check this by running the original implementation and or implementation. Okay, it seems that we were able to do an entire forward pass already. Yeah, I'm gonna add it to do here. Assert values, because we're gonna need to verify whether our implementation returns the exact same values as the original implementation. But yeah, we're already able to do a forward pass, which is a nice thing, on our cats image. But yeah, for now, I don't expect them to. So it returns last hidden states for now. Let's check their shape. And yeah, they are of shape batch size 257, sequence length, and then a hidden size of 768. But of course, yeah, for the moment we're not converting these query keys and values. So that's something we are doing here. Actually, we can include this now, I think. So again, the prefix thing here, I think we can remove that. And so basically what we do when we convert the queries, keys and value weights, so here this is just a single matrix, but then we need to split it up into query.weight, key.weight, and value.weight. So what we basically do is we take this, okay, so this already seems to be fine. We take this weight matrix, same with the bias, which is a single vector, and then we split it up. Okay, so this already also seems fine. Encoder.layer, and then 2 times attention. Yeah, so actually we can reuse this. Now we are basically adding those separate query.weight, key.weight, value.weight into our state dictionary, which we're gonna use to load our model with. So it actually seems that we are already converting the hidden states. All right, so now what I'm gonna do is first and for all, I'm gonna commit this and push it to GitHub. So convert all weights. And then the next thing we need to do is basically check whether the, so if I go back here to the DynoV2 model, we need to check now whether the last hidden state that we got here from our Hugging Face implementation returns the exact same values as the original implementation on our cat's image. So here we have a final layer norm and then a pooler layer norm. Okay, so now I'm gonna add here a print statement to our inference script. Well, we have the forward features method. Alright, so I'm just gonna add here shape of final hidden states. And then first values of final hidden states. And then I'm gonna just print out the first values. I'm gonna commit this. And I'm gonna rerun this on Colab Notebook. Because now we want to verify whether we have converted all the weights properly. There is of course a chance that there is a bug in our block, in our transformer layer class, or in the attention class. So now we can actually see, for example, here. So these are the first values that we need to get, minus 2.18 and so on. Let's see what we got here. I'm gonna also print out the final first values of final hidden states. So now we can actually see whether our conversion is done properly or not. And it seems that they are not the same. So here we got minus 1.21 and so on. Whereas in the implementation here, we should actually get minus 2.18. So in order to debug this, what I typically then do is I go to my Dyno v2 encoder class in this case, which is like applying these transformer layers. And then here, let's maybe just see. Okay. So here I'm just gonna add a print statement if e equals to 0. So for the first transformer layer, print the hidden states before first transformer layer. So that's gonna be hidden states 0, and then the hidden states after the first transformer layer. So now if you run this conversion script, oh, there's still missing keys. That might be a reason actually. But yeah, in any case, let's print out the same thing, but for this one. So here I can add the same print statements. So if, yeah, let's just call it E. If E is equals to 0, print out the hidden states before the first transformer layer, and then print them out as well after. Because if they gonna work, if it's gonna work for the first transformer layer, it's also gonna work for the remaining ones. So now I'm gonna rerun our inference script. And then we're gonna do the same. So these are the hidden states before the first transformer layer. Yeah, they correspond to the patch embeddings, as you can see. And then we have the ones after. So now let's see here what we got. So this still corresponds, it seems, minus 0.014, 939, minus, okay, this still seems to be fine, but then after we need to get 0.016. That doesn't seem to be correct for our implementation. Minus 0. Okay, there seem to still be a small bug somewhere. Yeah, they need to be like, those are still not the same, even though they are close. Like, of course, you need to make sure that when you convert weights that both are in the evaluation mode to turn off dropout, for example, but that's the case. Then the layer scale thing. Well, they are both using the same value. I'm not sure actually if layer scale is a deterministic thing. I think so. I'm gonna print here first values of hidden states after first residual. And then the same, but actually I don't want to print this for every block. So I'm gonna add here print values equals to false, and then if print values. And then after the second residual. And then in our forward features method, I'm gonna say here print values, but only when e equals to 0. So I'm gonna rerun this. So that's usually how I like debug a conversion of weights between the original implementation and the Hugging Face implementation. So now we want to see like how the hidden states look like after the first nested block tensor. Okay, so it looks like this class is being called and not the original block class. Attention bias. Get attention bias and concatenate. This is something we don't have yet. Maybe they have some special attention bias that was used. Actually, you could check the original paper for that attention bias. Nothing is mentioned on bias here. Okay, so here the forward is being defined, forward nested. If the instance is okay, yeah. The problem is that in this class here we need to add print values, and then we need to make sure that we can pass this. Right, so I'm gonna rerun this. After the first residual, after the second. Okay, so I'm gonna print the same thing for our implementation. So now, we're just comparing both implementations. Okay, so they seem to be already wrong. after the first residual. Gonna check if this is deterministic or not. Zero point zero 15. Here's 0.0. Okay, so here we have minus 0.0224. So it seems to be already wrong before the first residual. Might have to do with this layer scale thing. So let's see here before layer scale. Or maybe it has to do with the attention clause itself. Line of V2 attention. But this seems to be like a very regular weight wise. Okay, I'm gonna add the same print statements here. Okay, so here I'm gonna add apologies. Let's call it Z. Hidden states before first layer scale. So here, after the first layer scale, before the layer scale, Okay, so this is all fine. The issue is probably in the attention layer. Okay, so I'm gonna add the same statements here. So here, this is what we got after the first layer norm. But this already seems to be different. Did we do something wrong when converting the layer norms? Oh, wait. No, norm 1, norm 2, norm 2. Okay, so I found the issue. The issue was the layer norm EPS setting, the epsilon used by the layer normalization layers. So apparently it's important to make sure this EPS thing here is okay, so it's used for numerical stability and had to be set to 1e negative 6 instead of 1e negative 12. So now the only thing I need to still add, well, let's see the hidden states now. After attention, 0.16. This seems to correspond now. And then after the first transformer layer, let's see what we got. Yep, this seems to now be fine. So now if we go to our Dyno V2 model, so yeah, our Dyno V2 model is actually corresponding, yeah, a standard. We can also say, okay, this is equal to a Dyno V2 model in Hugging Face, or a VIT model in Hugging Face. So this is very similar to the VIT model that you can find in Hugging Face. So we provide them in both PyTorch and TensorFlow and JaxFlex. So this is just the vision transformer without any specific head on top. So we're not adding any classification head on top here. So if we, like this class is just going to return the final hidden states of this shape. So the thing we still need to add here is this layer norm. So here in the conversion script, let's call it the final layer norm. So in the original model, the final layer norm is just called norm.weight and norm.bias. Within our implementation, yeah, we need to call it layer norm.weight. And now we should actually be able to get the exact same final hidden states. So that's what we're testing here, these final hidden states. So these we can actually call them final hidden states because, yeah, after all of these transformer layers, we get the final hidden states. And let's see, so these are the first values of them. And if we go to the notebook here, seems that this is now returning the exact same values. Alright, so I'm gonna also commit this, make conversion work. So now we have actually converted all of the weights. So as you can see, if we convert it, so here we're currently still specifying strict equals to false because there is still actually an unexpected key, which is the mask token, but actually that's not required for inference with the Dyno V2 model. So here if we search for mask token, it's defined here, but I don't think actually it's being used. It's only being used when you provide masks. And during inference, we're not actually providing any masks, so it's actually fine. So here we can maybe add assert missing keys. Those need to be 0, but then the unexpected keys need to include the mask token. And then here we can already add an expected slice. So let's just copy them over from the notebook. And then we can say assert torch.allClose last hidden state 033 and then should be equal to this expected slice. And we get an assertion error. But yeah, oftentimes this absolute tolerance is set a bit high, so let's maybe set it to 1e-5, which is already okay. It's still not passing. Let's see if it passes with 1e-4. Okay, that passes. So yeah, that's like by default tor.allclose uses like a very strict absolute tolerance when comparing the values of two tensors. 1e-8. The NOR case it's only passing when we have 1e-4. But yeah, that's actually like a minimum requirement. Sometimes it can be 1e-3, but yeah, other than that, usually it needs to have such a strict assertion. Alright, so then yeah, the next thing we're gonna need to do in our list here. So now we've basically done these steps. We've now implemented the model in the Hugging Face format. Yeah, making sure that the output hidden states and output attention flags are supported. That's the case. So in any Hugging Face model, you can always pass here when you do a for pass. You can say here output hidden states equals to true, for example, and output attentions equals to true. So that's supported. And then writing this conversion script. That's being done. So then the next step is gonna be implementing the tests for the model, implementing the preprocessor, which is gonna be used to like prepare the images for the model, implement tests for those as well, write documentation, and then finally open a PR on the Hugging Face Transformers library. So yeah, I'm gonna also commit this improve conversion script. I'm also gonna run make fixup now. So make fixup is like basically gonna run a bunch of formatters and code checkers for us. So for example, in this case, when I run it, it says that there is a redefinition of rename key. It seems that this function is indeed defined twice. Because yeah, when we're gonna open a PR on the Hugging Face Transformers library, we need to make sure that all of those checks pass. As you can see, it basically does a bunch of stuff. Like in this case, it's adding Dino v2 here to the configuration auto file. It's adding a bunch of image processor classes. Here it seems that quite a lot of stuff. Yeah, we can now remove the print values thing. So in our modeling, let's remove print values here. All right. And it's complaining no space left on the device. Wait, what? Is my Mac full? Oh yeah, sorry, I'm not running this locally. I'm running this on a remote machine. Okay, yeah, I'm gonna clean up some memory on that machine. But in the meantime, yeah, we've basically completed now the first 4 steps of this list here. So we're now finished with implementing the Hugging Face model and converting the weights successfully. So in the next video, I'm gonna move on and implement the test for the model, and perhaps also do the subsequent steps. So see you in the next video.